So this is the prototype for the pocket speaker amplifier. So when I originally started working on this project, the idea was just to build a speaker amplifier and then have you buy your own speakers and hook it up to that amplifier. These particular speakers, I got them at surplus store for $10. They're not bad, but they're not that great either. It turns out, if you know a little bit about speaker design, you can build much better speakers. And the other thing is, if you know exactly the response of your speakers, you can tailor the response of your amplifiers through filtering and get a perfectly flat response. So the thing is with amplifiers, if you're trying to design an amplifier that has a flat response from say 20 hertz to 20 kilohertz, it's actually really easy. Well, not really easy, but relatively easy. Compared to if you were trying to design speakers that had a flat response from 20 hertz to 20 kilohertz. It turns out it's basically impossible to do it with modern speakers. So the idea is if you know the response of your speakers, you can tailor the response of your amplifier through filtering and get a relatively flat response. So this is Parts Express. They offer a bunch of speaker building components. It's a really good resource if you want to get started with speaker design. So this is the one I'm looking at. And one of the other reasons I'm looking at this one is if you buy it in quantities up to 10, it's $21. But then 50 and up, the price drops by like 30–40% to $14. So much cheaper in quantity.
How big is the speaker?
It's 3.5 inches. So the final, where'd it go?
Yeah, right there.
That's it? Okay. How do I,
What do you want?
I don't use Max. Can I make it, well, I guess I can just, oh yeah, there we go. That'll work. I was trying to make it full screen, but, yeah. That's really a look inside. Okay. All right, so the data sheet basically gives you all the information on the speaker driver itself. So pretty much when you're designing a speaker, there's two things. There's the driver, and then there's the enclosure that the speaker driver goes in. So for this, the big wood box is the enclosure, and then that's the driver, of course. So in data sheets, what they do is they give you all these specifications, and they're for the speaker in what's called an infinite baffle. So it's essentially an infinitely large box, and then they give you all these parameters that tell you the response of the speaker system in that infinitely large box. So the theory behind it is if you know how it performs in an infinitely large box, then when you put it in a regular size box, or you reduce the size of the box, you know exactly how the response is going to change, and you can calculate what the response is going to be. So this graph right here basically gives a frequency response of this driver in an infinitely large enclosure. And basically what happens is if you know anything from about filter theory, if you took like ECE 202 for example, it's pretty much a high pass filter. So the high frequencies it passes, but then when it gets down to low frequencies, it starts rolling off. Basically what you can do is you can look at the slope of the roll-off, and if you calculate it, it's actually exactly 40 dB per decade. So the speaker itself is like a second-order filter. So the neat thing about that is you can approximate it with an electrical circuit. There's actually, this was figured out by two electrical engineers from Australia actually in the 1970s. And they figured out that taking a couple of simple measurements, you can represent an acoustic system, a speaker, as an electrical equivalent circuit, and then do all the design in something like PSpice, which makes it really easy for electrical engineers. Yeah, so I mean, essentially boils down to filter design. You have cutoff frequencies, you have cues, so and then as you change the size of that box, your response changes, your cutoff frequency changes, the frequency response changes with different cues. So the basic idea, we have this response. If we know this response, we basically approximate it as a smooth response. And then we say, well, hey, what if we make our amplifier response like this? So basically we can where the bass starts to roll off in the speaker, we can compensate for it by increasing the bass response of the amplifier. So, I mean, it's nothing new. I mean, it's basically just equalization. But the idea is if you know the exact point where the frequency starts to roll off in the speaker, you can match that exactly with the amplifier and get a relatively flat response. So kind of the trickiest thing is you can't do this with all speakers, because basically when you have a real small speaker and you start trying to push a lot of bass through it, as you go lower and lower in frequency, distortion goes way up. So you have to have a driver that can handle a lot of what they call excursion without distorting. So, and these are just, these are the parameters, the electrical parameters I was talking about. They call them teal small parameters after the two Australian guys that discovered the theory behind it. So, just one more thing I want to talk about. When you think about how a speaker works, you know, basically you have woofers and you have tweeters. So a tweeter is good for high frequencies, right? And then a woofer is good for low frequencies. So the commonly held perception is that if you want good bass, if you want lower frequencies, you need a real big speaker, right? Everybody agree with that? So it turns out that it is actually possible to get good bass with a small speaker, which is exactly what I'm trying to do with this project. So what it boils down to is a speaker, basically all a speaker does is it moves air. And as you get lower and lower in frequency, it has to move a lot more air. So the bass response basically depends on how much air the speaker itself can move. So you can do that basically two ways. The one everybody's familiar with, you increase the size of the driver. And so each movement of the driver pushes more air, right? Because it's more the area of the cylinder, or the area of a sphere, sorry, the area of a circle. As it gets bigger, the area gets a lot bigger. The other way you can do it, though, is you can increase the maximum distance that the driver can move horizontally. So in each pass, it pushes more air out. So the reason I chose this specific driver is that, okay, here we go. So the linear, what they call excursion, how much it can move outward is 4 millimeters. But it can go all the way up to 20 millimeters, so 2 full centimeters without a serious amount of distortion. So if you do the calculations, you're basically calculating how much air it can displace in one movement. A 3.5-inch speaker that has 20 millimeters of displacement is equivalent to a 6-inch speaker that has only 7 millimeters of displacement. So basically, you increase that displacement and you increase the effective area of the speaker. So basically that. There's actually a cool video on YouTube I can maybe show you that kind of gives you an idea of. Okay, so this is the exact speaker I'm looking at. There's basically. There's basically 2 ways you can run out of power in a speaker. If you get too high in frequency, basically you're moving it back and forth really fast, and so it ends up heating up a lot. And it's called thermal power limit. So basically, if you try and put too much power into it, it just gets too hot and burns up. So tweeters normally they're limited by thermal power. So that's why they, like, you see a little tiny, like 1-inch tweeter or something, can go up to 100 watts. That's the reason, because it can take a lot of heat basically. If you have a subwoofer, it turns out that the limiting factor is not heat, it's actually excursion. So it's going to hit that limit of excursion a lot sooner before it hits the heating limit. So if you can actually find a speaker like this one without much excursion, without clipping, then the idea is you can get more bass. There was another video here. So when I said when it clips, does everybody know what that means? I mean, when it goes too far and it basically hits a wall and it just stops. There's a video where somebody was kind of overdriving it, and you can hear it actually like when it goes to each side, you can hear it just hitting and hitting and hitting, and they're running it at like a 10 hertz generator, so you can hear every time it hits back and forth. So it kind of shows you what happens when you overdrive a speaker. Oh, this is it.
This is another Wing Krish production.
So he's running it through a refresh. So he's running it through a
This is another Wing Krish production, and
so he has it hooked up to a signal generator, and then he's just sweeping the frequency.
I got a Dayton 30 watt RMS subwoofer. It's 4.5 inches. It's actually large. It's I'm running a frequency generator at 6 hertz right now. So what you're seeing is actually live. It's not slowed down or anything. The speaker's great. I'll adjust the frequency generator so it'll create a summon. Here we go.
Is that right one? So you go up higher, it's fine, but then
I think it goes down to 1 hertz.
That's cool.
Yeah, so if you have any questions, email wingchristian@gmail.com or just go to my website at wigchris.gk. Thanks and have a nice day.
yeah. So that's basically what distortion sounds like when you're hitting that limit of the maximum excursion. So. Any questions?
How big, so what design of the speaker, enclosure, how are you trying to do?
So it turns out this one, the response is actually perfect in an infinitely large box. So it's real difficult to make that portable. It turns out you can actually approximate it pretty well with a 12-inch by 8-inch, or no, 12-inch by 8-inch by 5.5-inch speaker box. So it's not really portable, but it's the size you could fit on your desk maybe. And it basically approximates this, what they call infinite baffle response. But there's another problem when you do that. Like some speakers, they rely on a certain volume of air within the speaker box. And it uses that to basically counteract the force of the driver moving. And if you don't have that, some speakers can run into trouble. So I haven't built them yet. I'm thinking what I'm going to do is build one in a large box, so basically the infinite baffle type, and then another one in a smaller box, like a 3-inch by 3-inch by 3-inch, like the commercial, like home theater box type speaker size you would see. And what they call that air suspension, because basically you have a little trapped volume of air that the driver uses to counteract the force of the speaker moving. So, but then that introduces all sorts of problems in your in the frequency response of the speaker, and then a lot of other things you got to consider. The efficiency goes way down, so you have to have a more powerful amplifier to drive it when it's in a smaller box. But manufacturers love it because box material is real expensive. So if you have to add another couple cubic feet of box material, it could cost the manufacturer millions of dollars if they're making a whole bunch of these speakers. But I mean, it all just comes down to trade-offs. Like if you're willing to give up the size of the enclosure, you can get a lot better response. So, any other questions?